Morning, folks. How are we doing? Let's wait a few moments till everybody comes in. Questions in the meantime? Anyone? No? Questions, anybody? Yeah, when is our last lecture? That's a good question. Officially, classes end on December 3rd. That being said, this is an elective. I'm sure you're feeling the crunch of the end of semester. So my plan was to finish on Wednesday in 2 days. So Wednesday this week will be our last lecture. So here's my suggestion to you. If you have questions, come armed with questions. We can, well, it's all good. It's all good. You can watch the reruns, right? No, but seriously though, I want to give you time to do whatever you need to do in your other courses, and make sure you finish the semester on a high note. So yeah, so we'll have class today. We'll have class on Wednesday. That will be our last class. Come on with questions. We can review anything you want to. Otherwise, we'll discuss a few loose ends. And that'll be it. Today, we're going to talk about some open problems. Easy to state conjectures, which nobody has been able to prove yet. And the first one we're going to discuss is known as the Causality conjecture. What does the Causality conjecture say? Take a natural number. If it's odd, multiply by 3 and add 1. If it's even, divide by 2. So take a natural number. Let me define a function so that it's easier to keep track of what we're talking about. What are we saying? If n is odd, multiply by 3 and add 1. If n is even, divide by 2. And repeat. Right? Whatever you get out of that, it's going to be a natural number. And we can repeat this. Let's take an example. Suppose you start with n equals 3. 3 is odd. So we're going to multiply by 3 and add 1. What do we get? 3 gets sent to the number 10. 10 is even, so we're going to divide by 2. 10 divided by 2 is 5. 5 is odd, so we multiply by 3 and add 1. 15 plus 1 is 16. 16 is even, so we divide by 2. 8 is even, so we divide by 2. 4 is even, so we divide by 2. 2 is even, so we divide by 2. And we get 1. The conjecture is that no matter what you start with, you eventually get back down to 1. Let's take another example. Consider 7. 7 is odd. We're going to multiply by 3 and add 1. What do we get? 3 times 7 is 21, plus 1 is 22. 22 is even. We divide by 2. 11 is odd. So 3 times 11 is 33, plus 1 is 34. 34 is even. So we divide by 2. 17 is odd. So times 3 is 51. Plus 1 is 52. 52 is even. So we divide by 2. 26. That is even again. So we divide by 2 and we get 13. 13 is odd. So times 3 is 39. Plus 1 is 40. That's even. That's even. That's even. And now we have already encountered 5 before, so you know that it goes down to 1. How are we doing here? Right? Very interesting conjecture. We want to do one more. What's a nice number to take here? We haven't encountered 9 yet. Why don't we look at 9? 9 is odd, so multiply by 3 and add 1. 9 times 2 is 27, plus 1 is 28. Which is even, so we'll divide by 2. Which is even again, so we'll divide by 2. And now we're already there. So you know that that's going to eventually get back down to 1. How are we doing here? Questions? Anybody? So you can have fun choosing your own number and following this rule of multiplying by 3 and adding 1 if the number is odd, and dividing by 2 if the number is even. the claim is that eventually you get back down to 1. When we were discussing the axioms of mathematics last time, somebody had mentioned the Goldbach conjecture. What does the Goldbach conjecture say? Every even integer greater than 2 can be expressed as the sum of 2 primes. Let's do the first few together. So even numbers. Let's start with the first even number bigger than 2. So 4. How can we express 4 as the sum of 2 primes? Well, of course, 2 plus 2 is the obvious choice. What about 6? I'm sure you have it already, right? 6 is 3 plus 3. What about 8? Well, it's 4 plus 4, but of course 4 is not a prime. Instead, how are we going to decompose 8 as the sum of 2 primes? As the sum of 2 primes. 3 plus 5. 10. It's easily seen to be 5 plus 5. It's also, of course, 3 plus 7. The decomposition is not necessarily unique, right? There may be more than one way. 12. 12 is as the sum of 2 primes. 5 plus 7. Let's do one more. 14. Well, that's an easy one. All right. 7 plus 7. Maybe one more. 16. 16. Your thoughts? 11 plus 5. Also, 13 plus 3. Thank you, Jake. Absolutely. Right, again, the decomposition is not unique here. Right, so you see what's going on, right? Easy to state, easy to verify, but this has not been proven yet. consider the twin prime conjecture. Which says that there exist infinitely many primes p such that p plus 2 is also prime. Let's convince ourselves with a few examples. Three and five, right? What do we want? We want primes that differ only by 2, right? If you have a prime p, then the next odd number should also be prime. So 3 and 5, 5 and 7. 7 and 9 don't work because, of course, you know that 9 is not a prime number. So 9 doesn't work. 11 and 13. 15 is not prime, so that's out. But 17 and 19 are both prime. 21 is not. 23 is prime, but 25 is not. 27 is not prime, but 29 is, and so is 31. And so on, right? So you have these pairs of primes. The question is, are there infinitely many? There's a beautiful result of Zhang that took everybody by surprise in the spring of 2012. Who showed that there exists a natural number n and in fact he showed that n was less than or equal to 70 million. For which there are infinitely many primes p such that p plus n is also prime. Right, in the twin prime conjecture, the idea is that n should be 2. He wasn't able to prove that, but he did prove that there exists some n for which p and p plus n are prime. And then, not too long after that, Terence Tau, who is largely regarded as the best mathematician alive, Terence Tau, along with a polymath project. And what is that? Thanks to the internet, people have started putting things up and asking other people to collaborate. Try something, give us results, post proofs, ideas, and so on. So with this polymath collaboration, he was able to bring what was he able to do? He was able to bring the n to at most 246. So from some number less than or equal to 70 million, brought that down to 246. So very interesting idea. Let me mention that there is a largest known twin prime pair. So this number, or these two numbers, right, plus or minus 1, so they differ by 2. These numbers have $200,700 digits. So huge numbers. Numbers with 200,000 digits, right? Going back to what we were talking in the beginning of the course, right? Large numbers being very difficult to factor. Here we have two such numbers that are actually prime numbers. Let's start with the definition. A Mersenne prime right, so we're defining a Mersenne prime, a prime number of the form 2 to the n minus 1. say a few examples. If n is 1, this is 2 minus 1, and you know this is not a prime number. If n is 2, you get 2 squared minus 1. This is 4 minus 1, which is 3. In other words, 3 is a Mersenne prime. If n is 3, if n is 3, what are we looking at? 2 cubed minus 1, 8 minus 1 is 7. So 7 is a Mersenne prime. If n is 4, 2 to the 4 minus 1, that is 16 minus 1 is 15. This is not prime. Let's do one more. If n is 5, this is 2 to the 5 minus 1. This is 32 minus 1 is 31. 31 is a prime number. So this is a Mersenne prime, and so on and so on. I'll let you continue on. Here's before we ask the question, let me point out a few things. An easy observation. Observe that if n is not prime, then 2 to the n minus 1 is not prime. So I didn't have to bother with 2 to the 4. We knew it was not going to be prime. Why is that? Suppose n factors as a times b, where a and b are not 1. Right, so it doesn't factor as 1 times itself, but factors as something smaller. 2 to the n minus 1 is 2 to the ab minus 1, which is 2 to the a, the whole thing to the b. Right, because that's how exponents work, right? The power of the power, you multiply the exponents. Replace 2a by x, and we get x to the b minus 1. And now, if you take a step back, you see a factor. You see a root, right? X equals 1 is a root. What does that mean? If x equal to 1 is a root, then x minus 1 is a factor. So this is going to factor as x minus 1 times something else. You could do the long division if you wanted to. Right, this factors as x minus 1 times something else. A polynomial of degree b minus 1 This is always true. There are no exceptions, and we're proving it right now, right? If n is not prime, then, right, by replacing x with 2 to the a, you get x to the b minus 1, and you see that x equals 1 is a factor, right? X equals 1 is a root, so x minus 1 is a factor. So this factors as x minus 1 times that, and now if you replace back, x is 2 to the a, and there you have it. You have your number 2 to the n minus 1, which factors as one thing times something else. And this is not 1, right? Because a is not 0. So this is a number, and then you have another number right here. So no exceptions. There it is. Right, so a nice observation. And now, so, right, I mean, in your search for Mersenne primes, all you have to do is restrict your attention to powers that are themselves prime numbers. And now here's the open question. Well, before we talk about the open question, let me point out that it's important not to read too much into this, right? What we have shown is that if n is not prime, then this is not prime. This doesn't mean that if n is prime, that this will automatically be a prime number. That is not true, and the counterexample, you have to go all the way up to 11. 2 to the 11 minus 1, which is 2047, is actually 23 times 89. So even though 11 itself is prime, 2 to the 11 minus 1 is not. And now here's the open question. Are there infinitely many Mersenne primes? That's the open question. Are there infinitely many Mersenne primes? Are there infinitely many primes of the form 2 to the n minus 1? Right now, there are only 51 known Mersenne primes. The largest being 2 to the 82,589,933 minus 1. This was found recently, December 21st, 2018. So not even 2 years ago. This is a number with almost 25 million digits. If you're interested, you can join the search for Mersenne primes at mersenne.org. There is money to be made here. If you find just another Mersenne prime, $3,000. If you find a Mersenne prime with, right, I mean, this one has 25 million digits. The race is on to find a Mersenne prime with 100 million digits. The prize is 150,000. And if you're the first person to find a Mersenne prime with 1 billion digits, the prize is 250,000. So, certainly worthwhile. How are we doing? If you go to this website, they have a program which you can download to help you search for a Mersenne prime. My understanding is that if you're using their program, they're going and you find a Mersenne prime with 100 million digits, I think they want a percentage of the prize. I think they're giving you 50,000 and keeping the rest. But for somebody that doesn't have any programming experience and doesn't want to program their own search engine, it's certainly a worthwhile endeavor. So big money awaits over there. Questions here? How are we doing? Definition. A Fermat number who funds these prizes. I think it's a non-profit organization. They have a little bit of money. And yeah, I mean, in particular, I think if somebody from their organization won the 100 million digit Mersenne prime, because that's being paid by somebody else, then they would already have $100,000 available there to fund other prizes, right? So 3,000 just for any Mersenne prime. They can fund a lot with 100,000. Fermat number is any number of the form 2 to the 2 to the n plus 1. Where did that come about? Right, in the Mersenne prime, we were looking at numbers of the form 2 to the n minus 1. Right, and asking for what values, or really we were asking the question, are these prime? Here, we can ask the obvious question, what about 2 to the n plus 1? Right? Is this ever prime? Right, that's the obvious question, right? In the Mersenne prime, we're looking at this. So, if you couple that with the twin prime conjecture, the obvious question is what about 2 to the n plus 1? The idea is this: if n here's the claim. In order for this to be prime, we need n to be a power of 2. Right? Which would bring us back to the Fermat number situation. Let's prove this, because the proof is fairly straightforward again. Very similar to the proof in the Mersenne prime business. Right? Where we had to prove that, where we showed n had to be prime in order for 2 to the n minus 1 to be prime. Here, kind of the opposite, right? N has to be a power of 2. So consider 2 to the n plus 1, where n factors as a times b, where a and b are less than or equal to n. Could be 1. And b is odd. So if this is not strictly a power of 2, then it has to be a product of an odd number with something else. It could be prime, right? And could be prime, so this would be 1 times the prime number, and b would be odd. Unless, of course, n was 2, but then we're back in this situation. And we're going to do the same as before. 2 to the n plus 1 is 2 to the ab plus 1, which is 2a to the b plus 1. Almost the same proof. And now we're going to replace 2 to the a by x. So this is x to the b plus 1, where b is odd. So what happens if you replace x by -1? -1 to an odd power is -1. -1 plus 1 is 0. So x equals -1 is a root. So x plus 1 is a factor. So this factors as x plus 1 times something else, x to the b minus 1 and stuff. And there it is. This is 2 to the a plus 1 times other stuff, 2 to the a to the b minus 1. So one number times another. In other words, 2 to the n plus 1 is not prime. So once again, in order for a Fermat number, right, in order for a number of the form 2 to the n plus 1 to be prime, n has to be a power of 2. And so we get this. Now here's the question. So first of all, let's look at these. If n is 0, what are we looking at? This is 2 to the 2 to the 0. 2 to the 0 is 1, so this is 2 plus 1, which is 3. This is a prime. If n is 1, 2 to the 2 to the 1, this is 4 plus 1, which is 5. Again, prime. If n is 2, this is 2 to the 2 to the 2. This is 4, 2 plus 1. 2 to the 4, 4, 8, 16, plus 1 is 17. This is again prime. If n is 3, 2 to the 2 to the 3. This is 8, 2 to the 8. 4, 8, 16, 32, 64, 128, 256, 257, which does turn out to be prime. And I'll let you work out for n equals 4, 2 to the 2 to the 4, 4, 8, 16. So this is 2 to the 16 plus 1. So whatever that is, I'll let you work that out. But it does turn out to be prime as well. So now, you might be led to believe that they're all prime and everything works out nicely. And it actually did take quite a while to figure out that the n equals 5 is not prime. And in fact, the claim is that from 5 onwards, they are not prime. 2 to the 2 to the n plus 1 is not prime. For n greater than or equal to 5. So you see, that's quite interesting. All you would need to do here, if you were to tackle this question, would be to find a number which is prime, a number of this form which is prime. Very little is known because the numbers get so large so quickly here. But yeah. A counterexample would do the trick here. Show that this is not prime for some value of n, you're done. How are we doing here? Questions? Let's consider one last one. The Erdős-Strauss conjecture. What does the Erdős-Strauss conjecture say? For every natural number bigger than or equal to 2, you can write 4 over n as the sum of 3 positive unit fractions. What does positive unit fractions mean? So your 4 over n can be written as 1 over m plus 1 over k plus 1 over l, where m, k, and l are natural numbers. So fractions 1 over something, where these are natural numbers. Not fractions or anything, that would be trivial. Let's take an example. Right, so for any n bigger than or equal to 2, we're looking at this. So in other words, 4 over 2 here. 4 over 2, which is of course 2. Can we write 2 as the sum of 3 fractions where 1 is the numerator? Well, 2 is of course 1 plus 1. So we'll leave this one alone here as 1 over 1. And then this other one, let's split that up into 2. 1/2. 1/2. Right, so I've written 2 as the sum of 3 fractions where the numerator is 1. Consider 4 over 3. which is easily seen to be 1 plus a third, right? So this 1 could be thought of as 1/2 plus 1/2. And then you're done. Or you could also think of it as your fraction 1/1, and then this 1/3, we can split up as 2 pieces of 1/6. So already you have options, right? The decomposition is not necessarily unique as long as you can decompose. Four over 4, right? Which is 1. Well, that's easily seen to be 1/3 plus 1/3 plus 1/3. What about 4 over 5? Can we decompose 4 over 5 as the sum of 3 positive unit fractions? Anybody see it? It's not obvious. Not obvious at all. If we start with a 0.5, in other words, if you brought that over there, you get 3 over 5, which is 0.6, which is 1/2 plus 1/10. Perhaps that's what Jag was suggesting. I think this works out nicely. Let's check. If we bring everything back over common denominator, what do we get? We get 2 plus 5 plus 1. So that is 8 over 10, which is 4 over 5. There it is. And so on and so on. I'll let you play around with that. They get increasingly more difficult. But at the same time, there's usually more than one decomposition. So I'll let you play around with that. Let me point out observe that if n is even, if n is 2k, 4 over n, which is the same as 4 over 2k, or 2 over k, is trivially 1 over k plus 1 over k, and this 1 over k, you can split that up into 2 pieces, 1 over 2k and 1 over 2k. So this 4 over n trivially decomposes into that. So there's no need to look at even numbers in the denominator, right? You can restrict your attention to odd numbers. And in fact, so you can restrict your attention to odd n, to odd denominators n, and in fact, if n is composite, and the claim was true for smaller values of n, for values smaller than n, then 4 over, let's say, b has some decomposition. And then you can just multiply by 1 over a. And you'll have the decomposition of 4 over n. In other words, you can restrict your attention to prime numbers in the denominator. So instead of looking at 4 over n in general, you can, if you prove the result is true for 4 over p, that is sufficient. So you can right away assume that the denominator is a prime number. If it's true, if the result is true for 4 over p, it's going to be true for any number. How are we doing here? Questions? Anybody? Play around with these. You know, these are great fun. Convince yourself, try to see what's really going on. Try to understand what's happening. You know, I mean, here's the thing. Some of you might think, and some of you might be told, in fact, you know, these have been around for so long, nobody's been able to prove them because they're probably very difficult to prove, if not impossible. But, you know, I've always felt that a good idea goes a long way. And maybe these questions are just missing another approach. These questions might just be missing a nice observation, something nobody has thought of before. Maybe these questions are waiting for you. So play around with these, see what's going on, and we can discuss this again on Wednesday. For those of you who may have missed the beginning, Wednesday will be our last class. So come armed with questions if you have them, stuff you want me to go over. Otherwise, we'll tie up some loose ends and that'll be the end of it. Thank you all for coming, and I will see you all on Wednesday.